Jai Hind all, this is Assistant Professor Gagandeep Singh from Ajay Kumar Garg Engineering College. This is a VLSI technology lecture series with a course code of KEC 053 in AKTU. This is a series of complex topics, and in the last topic we have discussed Unit 1. Now this is a Unit 2 topic where we will discuss one of the method for epitaxy, and then what are the effects on the doping on this epitaxy. In the main lectures, we have discussed that epitaxy is required for basic applications like providing mechanical support to the layer that are grown through the epitaxy. So there is a wafer over which we produce some layers for the growth of the devices. These layers are grown very thin, and when these thin layers are there, then we need to have a support under that, and that is provided by the wafers, over which a process by which an amount of material that is set down by the crystal substrate, while the overall single crystal structure is still preserved, is called the epitaxy. So we have discussed in the main lectures also that in epitaxy the main focus is that we are overgrowing a layer over the wafer or substrate, and the main focus over there was that it should be a single crystalline structure, the same crystalline structure that wafer has, so that we can easily grow the epitaxy, and this process is done by the epitaxy methods. So this generally this we can say that epitaxy is the extension to the substrate lattice by overgrowth of the layer of the material that may be same or the different. The same type of material or different type of material, but we want that the crystalline structure of the both layers should be preserved. So there are different methods for the application or the growth of the bulk crystal for which are not enough for the BJT. For example, when we are growing a PNP crystal, PNP transistor, a crystal over which we will grow will not have the same thickness layers. The first N type of material that may be a larger thicker material. For example, for the collector, we need a larger N type of layer, over which we need some smaller layers. For example, the emitter will have the least thickness layer that can be grown by epitaxy, which is small layer. We have also seen that the epitaxy means when we work upon bulk material, that is called the epitaxy. So that work is that we are growing smaller layers. For example, in wafer layer, when we have created a wafer, it was a prepared through ingot, and generally it is a circular shape, and when we cut it into the smaller IC structures, it will be a thicker material. We have seen it is in the micrometers. So when we grow a smaller layers, then this layer that is grown over this will be a smaller, generally of a few microns of the size, is grown over this one. So the basic difference between the two layers is the thickness. In the wafer preparation, we do not grow smaller layers. The thickness is much more. Bulk material is much more, whereas the upper layer, the layers above this one are epitaxial layer, and they are of very few microns in size. Whereas the bulk material or substrate wafer is grown for the high hundreds of the microns, the epitaxial layer is of only few of the microns. Mainly, we have seen that the advantages of epitaxy is that it improves the performance of the uh, different type of the memories or the high density ICs. This is because the epitaxial structure may be used for the uh, smaller regions, smaller thickness layers. Also, we can provide the desired doping profile in by the epitaxial profile by including uh, different type of dopants in the epitaxial methods. Then we have also seen that in few methods epitaxial wafers offer a device designer uh, a control to the doping profile of the device structure. The doping profile can also be controlled. So we can include the doping. We can also control the doping in this epitaxial layer. The physical property, as we have seen that physical property of the epitaxial layer is different from the bulk material. The bulk material has the main task or main purpose to support, whereas for the epitaxial layer, as it is a very small layer, small thickness layer, so it cannot provide support to the epitaxial layer. It cannot provide the support to the different layers, but its main task is to provide the doping and the high other layer which are of the smaller size. The as the thickness is smaller, these two, carbon and the oxygen, which are main contamination in the preparation of the ICs. So these two should be removed. These should be avoided. So mainly epitaxial layers are free from oxygen and the carbon, which are the main contaminated. We have also seen that the epitaxy that can be classified based on the processes as the liquid phase epitaxy, vapor phase epitaxy, and molecular beam epitaxy. These two, liquid phase and the vapor phase epitaxy, has a chemical reactions involved. So these are also known as the CVD, chemical vapor deposition. Whereas Whereas in molecular beam epitaxy, we do not, the chemical reaction is not involved, and they are just by evaporation of the molecules of the depositing material on the wafers. So when we deposit, there are some impurities that are included in the epitaxy. So what are the effects of these impurities in the effect is? First thing, the hydrates of the impurity atoms, if there is any impurity atom that are produced by the impurity by the hydrogen, that will be the source of the reaction, because we know that the different reactions involved in the epitaxy use the hydrogen. So whenever there is a hydrates are available in the impurities, those will be uh, the main reactants in the reactions involve the epitaxy. So during the epitaxy, the surface should be clean, and it should be made completely free from oxygen and carbon. This will not only avoid the impurity, this will also it will also avoid the impacts of the damages on the different uh, surfaces that are available that are we are growing in the epitaxy. Now, when these effects are when these oxygen and carbon are there, these may produce a damage that may go all over the epitaxial layer, and also it may pitches in the also it may go inside the wafer. So this the damages that are present on the surface that may travel in the epitaxial layer also. For example, if there is an this is a side view of an wafer. So if there is a wafer and we have a some crack over here, and when a epitaxial layer, a smaller layer over is there, this is the damage in the wafer. This is damage in the wafer. Let's suppose a crack. When this damage is there, when epitaxial layer is grown over this damage, that will have do not have a mechanical support. When it will not have any mechanical support, this damage may propagate in the epitaxial layer too. So the damages that will be present in the lower layers, that will travel in the epitaxial layer also. So similar way, the patches of the oxides that are present on the silicon surface will also give the dislocations on the surface, dislocation in the epitaxial layer surface. So same again, if let's suppose this is a wafer, and some deformities oxides are there, then the epitaxial layer that will be grown over here will have some damages over here. So the patches that will be available, that will be on the wafer, that will be present on the wafer, that will be provide dislocations in the epitaxial layer also. So there is another problem that having the oxide as impurity. When oxide is there, they will have S2 O bonds, silicon oxide silicon bonds, which will have different radius. So this will have this will again produce a impurity that is larger in size. So when we have a few microns of the size of the epitaxial layer, then even a smaller impurity will have a larger effect on the epitaxy. This all impurities provide stresses on the epitaxial layer that will produce some dislocations and defects in the epitaxial layer. So first thing is that we should have a wafer which is clean, which is free of any damage and any uh, impurities. So we should have a perfectly damage free and oxide free wafer. This can be happen only by in situ cleaning. This is an important concept where we do not take the wafer out for the cleaning, but we take we give we gave this cleaning only in the reactors. So we do not take the reactor. We do not consider the reactor for the cleaning inside the cleaning. So this is generally done by the etching. This cleaning is done by the etching of the wafer, where in this etching we use hydrogen again and HCl is produced. This process involves HCl, so it is producing H2O, hydrogen, which can be used again for production of this involves HCl, which will result in production of H2, hydrogen. This hydrogen can be again used for the production of the epitaxial layer. So this reaction that is available is that we have silicon carbide, which will be reacting with the hydrogen to produce silicon plus twice of HCl. As this reaction is reversible, so in the etching process, this HCl will react with the silicon to give silicon carbide plus S2O. So we the silicon is developed over the wafer in the epitaxy by forward reaction, where we have a pure silicon that is deposited over the epitaxial over the wafer for the epitaxial layer. However, in the etching process, this reverse reaction is taken place. So we use HCl to produce hydrogen, and we etched out the silicon carbides. Now, when we want hydrates in the relatively higher volume, there is a reaction that takes place. This reaction is used for the doping in the epitaxy. So, doping in the epitaxy is due to the hydrates that are relatively stable. This is because of the available of the large volume. So these hydrates are available. This produce the doping in the epitaxy. The hydrates are relatively stable because of the large volume of the hydrogen atoms that are present in this in the reaction. For example, if we take a arsenic as a dopant, this will be easily absorbed on the surface, by decomposing and incorporating of the growth layers. The reactions involved are arsenic hydrates, which is a gaseous form. It loses hydrogen to give arsenic and the hydrogen, 3 molecules of the hydrogen. Now, this solid arsenic can easily lose electrons to give doping in the epitaxy. So, this arsenic is decomposing, and it is come in the epitaxial layer. Now, when it comes in the epitaxial layer, so there are some electrons available that may be used as the doping in the epitaxy. So, these hydrates are available, for example, hydrates of arsenic, which can be easily used for the doping in epitaxy. Now, in this figure, we can see that how this arsenic hydrates are reacting in the silicon to make a layer of silicons with the doping. There is a molecule of hydrate of arsenic, ASH3. This AH3 is when coming in the gaseous form, in the silicon, where we are using some method for the epitaxy. For example, for the vapor phase epitaxy, this can be easily included in the hydrogen. Now, this will decompose into hydrogen, 3 molecules of hydrogen plus arsenic. This arsenic will be doped into the silicon. For example, here two places are there, 2 molecules of arsenic are present over here, which is grown by the silicon. So here silicon is grown and arsenic is included in this process of epitaxy. The other molecule, 3 molecules that are available over here, that will be coming out because it is in the gaseous form. So this 2 molecules of hydrogen can be taken out and it can be used for the epitaxy again. So in this way, the arsenic can be used in the epitaxial growth. Now, in this doping, the first thing is that we have to model some impurities. So these models are given where impurity concentration is given versus with the silicon deposition rates. how much silicon is deposited with the concentration of impurities. As we know that as the impurity concentration is near to the surface, the rate will be higher with the higher concentration. So at the higher concentration, the rate of deposition is different. These are the experimental values and these are the modeled values, and this is the mean slope of this value. Now we can see that the deposition rate where it is more, approximately 2, the concentration is 10 is to power 15 centimeter per cube, where we have slope, the model and the experiment values are same. This will also a doping, which is there is also doping which is called the autodoping. This is due to the available impurities in the wafer. Now, when wafer has impurities, it is giving some concentration gradient between the wafer and the epitaxial layer. In epitaxial layer, the concentration of the impurity is 0, whereas if there is some impurity in the wafer, that will have a higher concentration. So the impurities may go from the higher concentration to the lower concentration, which is the concentration gradient. So when we are growing wafer to the then epitaxial layer, due to the concentration gradient, if the impurities come out of the wafer to the epitaxial layer, these are known as the solid state out diffusion, which is at the transition of bulk material and epitaxial layer impurity diffusion due to the concentration gradient. Another interface is the gas and the epitaxial layer. For example, if there is a again this is a wafer and there is this is epitaxial layer, and gas is flowing over here for the growth of the for example arsenic hydrates or the silanes. If gas is flowing over here, there is a first is the interface between these two. If some impurities are more over here, due to the concentration gradient, these impurity can go from the wafer to the epitaxial layer. Other way is that in this gaseous film, there will be higher concentration of the all impurities. So again, there is a concentration gradient between these at this interface. So the molecules may come out from the gas material to the epitaxial layer. This is known as the gas phase autodoping, where the doped impurity at the higher temperature, first of all, then it comes out and mix with the gas mixture. As gas mixture has a lower concentration of impurities, so it will come out to the gas. So it will give the change in the concentration of the epitaxial layer, and it is giving rise to the increase or change in the deposition of the over the epitaxial layer. So this will give the autodoping. This autodoping phenomena is important for observing the change, for observing the transitions in the different layers, different junctions. Now, if we see, there are two type of doping we have seen. One is the solid state out diffusion, and other is the gas phase out diffusion. Gas phase auto diffusion. So when we want a layer to be grown over the substrate, if this is the substrate over here, if this is a wafer or substrate, and we want to grow epitaxy over here, there will be some diffusion taking place from wafer to the substrate. So their concentration will be higher. So concentration will be higher. As we will move out from the wafer to the epitaxy, the concentration will be lower down, because the molecules that are coming out from the solid state to the wafer to the epitaxy, that will be decreasing. So it will be decreasing because the molecule will reach out by lesser width to the epitaxy. And at the surface again, at the surface of the gas and the epitaxy, the molecule will come out from the epitaxy to the epitaxial layer to the gaseous phase. So again, the concentration will decrease more drastically. So for example, here the concentration was decreasing like this one, but due to the gas phase autodoping, it will be decreasing like this one. So at a end where the concentration gradient is smaller, there the concentration will be constant. So in this way, the epitaxial layer, which should have a partitioning over here, or a separation between a wafer and substrate over here, it is moving from here to some other place. So if we again see, this will result in the different type of the junction. For example, if this is a junction where we have p type and this is n type, the concentration will be different. We want an epitaxial layer grown over here, so that we have a p type or n type different layer. Now, ideally we know that if we will draw any BJT, it is drawn like, or diode, it is grown like P and N. So we generally see it as a crisp boundary between the two junctions. But due to autodoping, the P type material will go into the N type, and N type autodoping will go from lower concentration to the higher concentration. So if we give the resultant over here, we will have a different type of doping. If we include the both type, this is for N plus and N type of doping. In N plus, the ideal we want that there should be a crisp boundary, but due to the auto doping, the N may be come out of this higher concentration N material, and it may go into the N. So it will giving a junction from here to here. So there is a shift of the junction between these two materials. And in the N-type material, there will be again a shift. The N-type material may be coming out of the epitaxial layer into the gaseous phase, resulting in a lower concentration. So as a result, there is a junction which is moving like, which is like a higher junction than a higher width than a lower width. So this will give a junction at the different place rather from the ideal one. So in this lecture, we have discussed the main process of epitaxy, how we are revised, we have how the epitaxy is done and what are the different type of the epitaxies. Then we have also seen the doping and the impurities, how impurities changes the epitaxy process. And then we have also seen that how doping is done, what is the effect of the impurities or the doping on the epitaxy. Lastly, we have seen that even if there is a concentration gradient in the wafer and epitaxy, there will be a doping that is known as the autodoping. Then we have also seen the effect of this autodoping by on the junction, how the junction is shifted from one place to the other place, from the ideal to the actual, due to the autodoping and the impurities present in the wafer. Thank you.